Olá pessoal, tudo bem? Sejam todos bem-vindos a mais um colóquio da Nano, a esse ciclo de seminários aqui, que é um evento da pós-graduação em nanociências e materiais avançados aqui da Universidade Federal do ABC. Antes da gente apresentar o nosso convidado, vou pedir para o Gustavo apresentar o nosso convidado, não esquecer que se você quiser que seu nome esteja na carta pública de comparecimento, é só você preencher o formulário que está no link aqui do Google Meet e também está no YouTube. Hoje eu estou sozinho, então se acontecer qualquer problema com o YouTube, provavelmente eu não vou conseguir resolver a tempo, mas essa apresentação está sendo gravada e vai ser colocada no ar assim que a gente terminar aqui no Google Meet. Então, Gustavo, professor Gustavo da UPIAN aqui da UFBC, você poderia apresentar o nosso convidado de hoje?
Claro, Pedro. Bem, eu queria dar as boas-vindas ao meu amigo Anderson Janotti. E eu conheço o Anderson já há tanto tempo que eu nem precisei fazer uma cartinha aqui com cola sobre o currículo dele. A gente interage já há mais de 20 anos. Na verdade, quando eu cheguei no Instituto de Física da USP para fazer o meu doutorado, foi o Anderson que me recebeu lá, me ensinou os primeiros passos da física, da matéria condensada. O meu primeiro artigo foi com o Anderson, inclusive, não sei nem se ele se lembra lá dos dímeros na superfície do germânio, lembra? Não, do silício. Claro. O Anderson, ele fez o doutorado dele no Instituto de Física da USP e em 2001 ele foi para os Estados Unidos fazer um pós-doutorado no National Renewable Energy Laboratory e acabou ficando por lá. Certo? O Anderson ficou um bom tempo na Universidade da Califórnia, em Santa Bárbara, e já faz algum tempo que ele está trabalhando na Universidade de Delaware como professor, onde ele montou o seu grupo de pesquisa. O Anderson tem alguns dos trabalhos mais importantes focando em defeitos em semicondutores. Então, hoje em dia, se você procurar as principais referências da literatura que ensinam a calcular defeitos em materiais semicondutores, a fazer simulações de primeiros princípios de defeitos em materiais semicondutores, certamente você vai cruzar com algum artigo que o Anderson publicou. Estava olhando aqui no Google Scholar, ele tem um review que tem quase 3.500 citações. Certo? Ele tem alguns artigos estudando defeitos em óxido de zinco, que são também altamente citados, mais de 1.000 citações cada um deles, e assim por diante, certo? Então, certamente é um dos maiores especialistas disponíveis aí para falar para a gente sobre defeitos em semicondutores e sua importância. Anderson, é sempre bom tê-lo aqui conosco, uma pena que você não possa vir presencialmente. O Anderson já veio aqui na UFBC outras vezes presencialmente, então é sempre muito bom tê-lo aqui, Anderson. Now it's up to you, Anderson. Welcome.
Okay, Gustavo, thank you. I said that I'm going to speak in English because my Portuguese is not great, but don't get your my English is also not that, but anyway. So, thank you, Gustavo, for the very nice introduction. Yes, I remember very well the early days at the USP, the Alberto Fazio's group, right? So I'm going to try to convince you that although defects in semiconductors is an old sort of traditional field, whenever you have a new material and we want to use it for electronics, optoelectronics, such as LEDs and lasers, high power electron solar cells, qubits now, right? Some defects are being studied as qubits for quantum computing. We do need to understand and control defects because they impact a lot of properties that are important in devices. So start just the same, because this is an old joke. When I decided to come to Delaware, and in California, they start to make, where, right, Delaware. And just for you, and I maybe many of you don't really know where it is. So we used to say that is in between New York and Washington. It's a long way, but yeah, it is in, very close to Philadelphia. A little bit further away, we have Baltimore. So if you come to Delaware, you probably fly the easiest way. The closest airport is Philadelphia International Airport. The mascot is really a chicken. It's a blue chicken. They say it's a mad blue chicken. And here are some fun facts. And as you know, we have the president of the United States come from Delaware, very close to the university here. Here's some photos that I'd like to show. Perhaps some students are watching. They may be convinced to come and spend some time with us here, showing the photo of the main campus on the left. And we have a new, called the Star Campus, in the south part, on the other side of the highway. And the IC lab, which is a state-of-the-art facility with a clean room, nanofabrication, and TM. And some important partnership now with the Chemours, which come from DuPont R&D. And I figure a nice stadium here that has been renovated. In the group, in our group at UD, we work on electronic structure theory of materials, solids, crystalline solids. And we like to say that we are working on materials that are related to energy savings, energy efficiencies, or quantum computation. These include wide and narrow gap semiconductors, semi-metals. Some of them are topological insulators, semi-metals. Some of them are multi-insulators. Now we are getting to the materials, and organic semiconductors, that is something that we would like to get into, not there yet. And most of the problems we are interested in, they are related to defects, point defects, interfaces, surfaces, heterostructures. And that are for basically, these are the basis for most of semiconductor devices that we know. And we calculated transition levels related to defects, surfaces, interfaces, states, reconstructions. We care about what happened in the interface in terms of bands, right? The band alignments that will tell us about quantum confinement in heterostructures for lasers, LEDs, defect-related optical absorption luminescence, and band gap engineering. Tune your band gap through alloying, also amorphous phases, and also we care about thermal and charge transport. We use known codes, right? Codes that are known to everybody. It's available. VASPA, beneath Quantum Espresso. And for some of the more recent work on very large systems, we are using valence force field with lamps. Defects in solids. You can think is any deviation from crystalline bulk materials. Traditionally, they have been divided in point defects. There are intrinsic point defects, such as a vacancy, as you can see schematically on the right side, interstitials, antisites, that means in a compound material, A-B compound, if A occupies a B site or B occupies a A site, we call it an anti-site. Complexes is the association of point defects. You can think of dye vacancy, for instance. Extrinsic point defects, you think about impurities. The most traditional one you can think of in semiconductors is phosphorus, dopants in silicon. They substitute on the silicon side and give away one electron, changing the conductivity. But you can have also impurities at the interstitial, such as lithium in silicon, for example. And the impurities, they also form complexes with either other impurities. For instance, magnesium and hydrogen in gallium nitride is a famous case, or with a defect. And there are many examples in the literature of an impurity bonded, right, or near a defect. So I will be focusing on the pointed defects. I'm not going to talk about extended defects, and these can be dislocations, stacking faults, and you can even think of surface interfaces, right? And yeah, so pointed defects in solids. There's a chapter in Kittel in the first edition where it derives the concentration of point defects just to take into account the configurational entropy. So, and basically what we conclude from that is that they are unavoidable. At the finite temperature, the entropy will force you to have a finite concentration of defects, right? So typically formation enthalpies of defects, they are positive numbers, because then they enter in exponential. If you want the concentration, especially in the dilute limit, the dilute limit is where the defects, they don't see each other. The concentration can be written as a simple Boltzmann form with the exponential of minus the formation energy divided by kT. Okay, here is just a derivation for a Frankel defect, which is, I think, is an interstitial vacancy pair. Okay. I like this paper very much because when I read it, I was in my PhD. And usually we think the defect has a negative connotation, right? But actually they are actually vital for semiconductors in many, many cases, right? For instance, doping, we use a doping, which is a defect introduced in a semiconductor, an impurity, to control electrical conductivity. And this plot is amazing, right? Because you see the resistivity of silicon, and you can see that you can change the resistivity by more than 10 orders of magnitude by controlling the doping concentration. It's one of the properties that change by several orders of magnitude, one of the few, I think, by just changing the composition. And you can imagine that, well, how much I'm changing the composition. So typical impurity concentration, doping concentrations, I would say, right, varies from 10 to the 14 to 10 to the 17. 10 to the 14 will be the low doping regime. 10 to the 19 is a high doping regime. And these, remember that the number of atoms per cubic centimeter is about 10 to 22, right, in a typical semiconductor like a silicon, right? But these doping, typical doping conditions, this limit is not strict. For instance, in transparent conducting oxides, which are wide band gap semiconductors, they can hold very, very large doping levels of 10 to 20 or 10 to 21 that corresponding to approximately 1% or few percent of dopant, atomic percent, right? For instance, tin doped indium oxide, often called ITO, you basically dissolve a few percent of tin so that you have a high conductivity. So tin is a donor, replaces indium, and indium has a very large gap, so the material is still transparent, and that is the name here, transparent conducting oxide, similar for aluminum dope, zinc oxide. What are the materials that are impacted by defects? First, electrical conductivity. You can dope the material p-type or n-type. Defects can compensate the prevalent conductivity. For instance, they can kill electrons, excess electrons or holes, right? And this can be desirable or not. If you want to make a semi-insulating layer in your semiconductor device, is probably desirable. But if you wanted to maximize your carrier density, it's probably not a good idea to have a compensation centers. It can also change thermal conductivity, especially at high doping levels. It can impact the electron phonon coupling. One that we usually forget, right? The luminescence, color centers, right? These are defects. In the case of ruby, we have aluminum oxide. It's not really a semiconductor. You can say it's an insulator. It's a very, very large band gap, but the color comes from these chromium impurities in aluminum oxide. Here's a picture here. In the case of light-emitting diodes or solar cells, you may have non-radiative carrier recombination through defects, which has a picture here highlighting the Shockley-Reed-Hall effect, where a defect level or a defect state in the middle of the gap may lead to non-radiative recombination through this process here in this configuration coordinate diagram. You can use the defects to increase ionic conductivity. That can be used in fuel cells, for instance. And all these point defects, they indeed mediate mass transport, and that, for instance, can be important in metal hydrides that have been studied for hydrogen storage. Basically, the hydrogen that moves for the decomposition of the oxide, for the hydride material, metal hydride, you start moving the hydrogen through point defects inside the material. Some more recent applications are related to memristors and oxygen vacancies in very thin layers of oxides have been invoked to explain these nonlinear IV curve for on and off of the device. Again, mass transport, again, charge and discharge in battery electrodes. Here is an example of a proposal that a lithium vacancy in lithium iron phosphate. Catalysis, for instance, oxygen vacancies on oxide surfaces. And more very recently, there is a driving force, maybe not that recently, the initial work started more than 10 years ago, a driving force to look at spin centers. So it's a defect in the material, like an NV center in diamond, with a well-defined spin state. And then you can read the spin state optically, initialize and reset, right? So this is you can think of, right, if you are more excited about that, right? You can think of using defect engineering to tailor the properties of your material, right? And here's an example. This is a paper just published, I think, last year, where they are talking about controlling oxygen vacancies in metal oxides. You can actually have a very broad range of applications: IO conductors, fuel cells, gas separation, membristors, gas exchange sensors, field effect transistors, right, quantum devices, spintronics. Here on the right side, you can see the range of defect concentrations for different experimental probe for defects. You see it goes from 1 ppm to a few percent here. And different materials, the structures, and different effects that you can see, right? So identification of point defects are quite challenging. Basically, defects are difficult to see. Okay, you don't have a powerful microscope to look inside your bulk crystal and identify an oxygen vacancy, for example, right? In most of the techniques, most often you require not only one technique, but a combination of techniques to identify a defect. And these results only provide indirect and sometimes even circumstantial evidence, right, of the presence of these defects, okay? Often you introduce the defects in the material to study it, right? And when you do that, you not only introduce the defect that you want to study, probably other defects, and then at the end you still have you're still not sure which defect you're looking at. There are many experimental techniques that have been developed along the years that can be used to study defects. I separate here in color codes. The blue is the electrical measurements, the red is optical spectroscopy, and the green is particle beam. I think my spell checker is wrong here. And the microscopy in orange, right? For instance, Hall effect, you can do Hall effect as a function of temperature, and you have carrier concentration as a function of temperature. You can, in the case of doped semiconductors, you can look at freeze-out cubes, extract and activation energy for your impurities. Capacitance voltage, or you can actually probe levels in the gap using your semiconductor as a dielectric, and you sweep, you have a contacts, you sweep the voltage, you can see a signal of a defect capturing electron, releasing electrons, basically. In this case, the sweeping time is long enough that the charge state, the change in the charge state is in between the relaxed configuration, local relaxed configuration for the different charge states. So you can measure transition levels, basically, also in deep level transient spectra, that you can actually calculate and compare with the experiments. Optical spectroscopy, you can think of infrared absorption due to, for instance, hydrogen impurities bonded to host atoms, right? But you also have electron parametric resonance that detected the spin of the center. Sometimes you can even couple it with optical probe, right, or optical excitation to actually excite it to a spin state that you can actually probe it. Particle beam methods, I want to highlight the secondary ion mass spectrometry because you can actually tell the composition. Although when you're dealing with defects, there's you only see those defects that you are looking for, right? The species that you're looking for. X-ray absorption emission, also you can identify impurities, but you have to be careful with the detection range, right? If you have a too low concentration, you don't see anything. And positron annihilation, that you actually introduce a positron and see how long actually you introduce a positron, and you look at the decay emitting alpha, emitting a high energy part that you can detect, and basically this positron measure empty spaces in the crystal, basically vacancies, and not necessarily a single vacancy. In many cases, it can be a void, right? So you have to be careful. But in principle, you can actually have a measure. You can measure single vacancies using PAS, positron annihilation spectroscopy. And for the microscopy, I would highlight the TEM, transmission electron microscopy. But you are probably aware that if you want, you have seen these figures of TEM picture, but it's a cross section usually, so you have to cut, right, the material, and when you cut, not necessarily you're cutting through a defect, and when you measure, you're not necessarily measuring one layer, but you're measuring a column of atoms and this column can be very thick, so you may have only an average effect, and this can be challenging to see actually point defects. So yes, experimental characterization of defects is difficult, and theory is here to help, right? Theory actually can not only it can complement in a way that very often you can predict. Now we are in a situation that we have a more predictive tool than before. I will comment on that, and but you also can give access. You have access to properties that are often difficult to measure. So I'm talking about the atomistic description. So I'm talking about atoms, right? And the lowest level of theory you can think is using empirical potentials, such as valence force field. And basically, you can imagine Lennard-Jones potential, and you solve Newton's law. So these are important tools that you can actually describe a system with a very, very large number of atoms. A million atoms calculation, I think you can push it for you. But you have only social information, right? So, and these potentials are difficult, very difficult to describe bond breaking, for instance, right? With these sort of potential. So, but if you really want to describe what's happening in terms of point defects in solids, you really need a quantum mechanics treatment, right? You need an approach. So this is the electronic structure theory. And the first thing you realize that, well, it's a many electron problem. And the first thing you learn when you learn in many electron physics is the Hartree-Fock method, right? Where your wave function is antisymmetric. You build it as a Slater determinant of single particle levels, right? And the problem is that you don't have electron correlation that beyond the exchange. You can call it the exchange some sort of correlation, right? And band gaps are too large. And the reason is that you have only one determinant. A very popular approach, very powerful, is the density functional theory. And the most used one still is the local, semi-local approximation to the exchange and correlation potential. But that you have a band gap problem. Basically, the band gap is much, much smaller than the experimental data. It's very often more than 50% smaller. And if you wanted to describe defects that they have levels in the gap of a semiconductor, you may end up with a very large error. You may only have a qualitative, sometimes wrong conclusions, right? You can draw only qualitative conclusions. But in the past 10 years, there was significant improvement. First with the DFT plus U, a little bit older, and hybrid functions. Now that they are very popular, and it looks like, although in my opinion it is sort of not a final theory because you are mixing two things like Hartree-Fock and density functional theory, I would say it probably goes in the right direction, because what it does is it makes your exchange from your local approximation non-local. You add a fraction of a non-local component to your exchange. In the density functional theory, of course, you do structural relaxations. You can do that in Hartree-Fock as well. And the limitation is, I would say, still you can do only up to 1,000 atoms. You can say, well, maybe that's enough, sometimes not enough. But 1,000 really you can do with DFT. If you go to hybrid functionals, it's too expensive still. The other method that you can think of, right, is this quasi-particle GW, where you can rigorously describe the energy to add or remove an electron in the solid, basically give you the ionization potential electron affinity. So if you imagine that you have a defect, you're probably probing the transition levels. However, since you have no structural relaxations, right, you have somehow to add and you don't have total energy, so you have to add these. You have to combine it with your DFT calculations. So for first principles description of solids, we start with the Hamiltonian, and we can write, it's easy to write, however difficult to solve. Remember that the psi here has to be antisymmetric with exchanging two electrons, right? So density functional theory came to help, right? In the work of Hohenberg-Kohn, 64, Kohn-Sham, 65, it laid out an approach that is nowadays computationally efficient, right, to calculate total energy of a crystal, let's say a system of electrons, in terms of the density, right? So it's a function of the density. And then in 65 came these ansatz of independent electron approximation by writing the density as a product of single particle orbitals, right? You can write an equation that looks like the Schrödinger equation for one particle, where your potential now depends on the density, right? So however, you still have a term here that you don't know, the exchange and correlation potential that is unknown. So in principle, it's an exact theory, but you don't know the form of the exchange correlation function. So the approximations to it, the first one is the local density approximation, already introduced by Kohn-Sham in 65. And the idea is that you take the exchange correlation from a homogeneous electron gas, right? So they parameterize it using quantum Monte Carlo calculations, and you have basically a local form for your functional. And later on, there was an improvement by including the gradient of the density. These two methods here, right, they're very similar. They give a similar results. I think, however, you can say that the GGA is probably more accurate for molecules, for instance. And that probably what brought the popularity to DFT in the chemistry community. The bottom line is, for crystals, lattice parameters you can get without any input from experiment. You can get lattice parameters within 1 or 2% of the experimental data, which is amazing already. But the band gaps are too small, either GGA or LDA. And for defects in semiconductor, this may be a big problem. So to overcoming, how to do we solve this problem, overcome this problem, band gap in DFT LDA. One of the first approach actually were developed for multi-insulators is adding an external interaction for a localized, let's say, flat bands, right? Low dispersive bands representing then localized states. So what we did that using LDA plus U was to correct the position or correct the position of the semi-core D states. At that time, we were interested in zinc oxide. So the zinc 3D band was very flat and low, very low in energy compared to the top of the valence band. But correcting that, you actually corrected the interaction of this band with the top of the valence band states, and you sort of increased the band gap. You can still get the total energies and forces. Lattice parameters is still well described within GGA plus U. However, there is you have to choose the U parameter. You can say you can compute it from first principles. Or what we did at that time was calculating it for the atom divided by the electric constant of the solid. However, it only partially corrects the band gap, okay, in the case we look at. And in terms of a computational effort is the same as LDA or GGA. And then at some point we started using hybrid functionals. They are much more expensive, 10 times to 100 times more expensive than LDA or GGA. These, because we use a plane waves to expand the wave functions in our code, right? Perhaps if you use a code that has a localized basis set, it may not be as expensive. This because you have to compute the non-local exchange from the focal operator, right? So there is a partial cancellation of the self-interaction problem in LDA GGA. This is a good thing. You corrected the band gap. In most cases, in some cases, you have to increase how much non-local exchange you add. You still can compute the total energies and forces, right? And yeah, the only drawback is that, well, one of the drawbacks is that it's much more computationally expensive. As I said, the GW has been available for some time. Nowadays, you see more and more GW calculations applied to semiconductors in general. Again, it's formally correct approach to compute band structures, provides additional removal energies. However, you don't have a forces, total energies are still in development, and they end up being much more expensive than hybrid functional. So for defects, they have limited use. Still, we did use GW combined with DFT to understand the color sensors in magnesium oxide some time ago. So let me show you how this is used in practice. Here, I show the band structure. That's usually what you show when you talk about the semiconductor. So energy as a function of the wave vector, right? And these wave vectors are inside your Brillouin zone, right? So gamma point is at the center of your Brillouin zone. In zinc oxide, the gap happens at gamma point. You see the conduction band in red, the valence band in green, and there is a small gap of 0.8 electron volts only compared to 3.4 EV that is the experimental data. The LDA plus U, using a U of 4.7 electron volts, give you a band gap of 1.5. And you see we did a calculation to understand what is the effect on valence band and conduction band separately, we found that it affects both valence band and conduction band. It's still not doesn't fully correct the band gap. And then when we compare it with hybrid functional, you see that hybrid functional give you the band gap very close to experimental value. We have to increase the mixing parameter beyond the 25% that is standard. But the results for the band structure at least shows that we can describe not only the band gap, also the position of the D bands with respect to the top of the valence band. Here I show a comparison with the photoemission spectrum here on the left. And what we found is that the effect of you can think, well, if you wanted to correct the band gap, isn't just shifting up the top of the valence band, and the answer is no. What happens is that you correct the valence band, in this case coming from oxygen 2p orbitals, right? Much more than what you corrected the conduction band in this case. And actually, if you compute the ionization potential for zinc oxide, you find that the hybrid functional take you the right direction. It gives you a very good agreement between ionization, calculate ionization potential with the experimental data, which is about 8 electron volts. So in defect calculations, what we do then, we say we construct a supercell. Basically, is a chunk of the material that we repeat in the 3D space. The supercell has to be large enough that the defect that you create in the middle of your cell doesn't interact with the defect in the neighboring cell in the image, right? In the image cells. So, and from total energy differences, right? You basically calculate total energy for your supercell with a defect, and you take the total energy of the supercell with defect and the supercell representing a pristine crystal, and you have a formation energy, basically. And what do we do with formation energies? So basically, the formation energy tells us how likely a defect will form. It can tell you about the defect concentrations. High formation energies means less likely to form, right? Charge state transition levels, you can derive it from formation energy difference for the same, for different charge states of the same defect, okay? You can, from transition levels, you can tell if a defect is acceptor or donor or shallow center or deep center. You can calculate the binding energies of complexes. For instance, if you have defects forming a pairing, right? You can calculate them separate and together and take the energy differences. You can, total energy difference, you can tell how likely they are going to form together, right? Example, hydrogen passivation in magnesium doped gallium nitride, which is now a classic case. You can calculate from total energy, you can calculate migration barriers. Basically, you define a path and you can calculate the total energy as you move the atom inside your crystal, representing in migration, right? And there are some details like how you relax the environment as you move the atoms across towards an equivalent site in the crystal, and so on. But you can calculate migration barriers. And also you can, for instance, in the case of, you can calculate frequencies of local vibration modes, basically. The case that comes to mind is the hydrogen interstitial in silicon. You can have the stretching modes that and the wagging modes, for instance, right? So defect formation energy you calculate as a total energy difference. And we also take into account, for instance, if you remove an atom from the crystal, where do you put it? Where is your reservoir? That is this mu I here, right? And usually we refer mu I to a standard phase of your the element that you're removing. For instance, if you're talking about zinc oxide, you can talk about zinc rich, and the zinc rich limit being a zinc solid, right? Zinc metal, or the oxygen rich limit being an oxygen molecule at a very, very low temperature. And also it takes into account the charge state. Q is the charge state. You can add an electron to the system or remove, and you always, the energy cost of adding or remove will depend on the Fermi level position. And this dependence is linear, right? So Q can be neutral, so zero, so there's no Fermi level dependence, or it can be +1, and you're going to see there's a curve with a slope equal +1 for a positive charge state, or slope equal -1 for negative charge state. This correction here is something that has been discussed along the years. It takes care of the fact that your supercell is still finite, right? And you wanted to extrapolate to the dilute limit. Dilute will be the defects, they are very, very far apart, right? Remember, you have a 100 atom supercell. So you can say that the defects, if you're not careful enough, the defects basically see each other, right? So this correction here takes that into account, and is a charge state dependent. It does no correction for the neutral, by the way. So this is a typical formation energy diagram. You have here is a formation energy on the y-axis, and the Fermi level on the x-axis, the horizontal axis. The blue represents Fermi level values already inside the valence band. The orange is the conduction band. So you usually draw from valence band maximum, VBM, to conduction band minimum, CBM. And you see, schematically, you can have a +1 charge state, slope equal 1, neutral charge state, slope equals 0, horizontal, right? No dependence on the Fermi level, and the negative charge state has a slope equal -1. The kinks in these cubes represent the transition level. So I have a donor level and an acceptor level here, right? The +0, the 0-. And it is important not to confuse these with the single particle energies that you see in your band gap, okay? So these here in this diagram, you can see them. These are Fermi level values, right? Where you see a transition in the charge state of a given defect. And you can see it, you can measure it using capacitance measurements or CV, right? Or deep level transient spectroscopy as well, right? Now, the single particle levels, you still can see them. Usually, for instance, in photoelectron spectroscopy, okay, you remove an electron from a state in the gap, right? But the position of the single particle levels not necessarily coincide with the transition levels here, okay? So the optical transition levels, they may be different from the thermodynamic transition levels extracted from these formation energy diagrams. And I will try to explain it a little bit more in the next slide. So I will skip this. So here you have a transition level. So you remember that when you probe the system optically, right, the optical transition is so fast that the system doesn't have time to relax. So you have, for instance, if you have a defect in the minus charge state, we represent by this curve here. In red, the slope equal -1, the solid one, right? You suppose you have an electron sitting on a single particle state in the gap. When you excite it, you can promote this electron to the conduction band. Okay, so this transition energy is basically, so you go from the negative charge to neutral, right, without changing the local geometry, right? The atoms, they don't have time when the transition happens, right? So this is represented by the blue curve here, right? Of course, after you are in the neutral charge state with an electron in the conduction band, your defect now relax, or and because these are emitting phonons, okay, and end up in the minimum here, in the upper part of this cube, representing the neutral charge state in its equilibrium geometry, and then eventually it emits, right? This emission takes a lot longer than the relaxation from the excited negative neutral plus electron in the conduction band and by the minimum. And eventually emits. This is the Frank-Condon shift, right? The difference between the absorption and emission. Okay, so this is what we call configuration coordinate diagram, right? So the bottom cube represents the negative charge state, and the parabolic shape here, the idea is that when you change the atomic positions, the energy changes as the square of the displacement, basically. You can think of a Hooke's law, right? And so from these transition levels, right, thermodynamic and optical transition levels, you can use it to predict and compare with experiments, right? So from formation energies, we can extract defect concentrations, right, through this simple Boltzmann equation, and we can compare it to SIMS measurements, sometimes Rutherford backscattering spectrometry. They give you an idea of impurity concentrations, often relative values, right? Electron parametric resonance, I think they can give you an idea of, again, the amount of defects that you have. Also, they tell you the chemical identity of these defects. Positron annihilation spectroscopy, they often give information about vacancies, and less common but harder to say, especially if you have a very small defect concentration, is dilatometry. And we can eventually compare with the local lattice, the local lattice relaxations, right? You can compare with sometimes with X-axis impurities, relatively heavy mass, G factors and hyperfine parameters that can be computed. They compare with the APR. Thermodynamic transition levels, they can be compared with the DLTS, right? Sometimes temperature Hall measurement, especially if you have a shallow levels, and vibrational frequency. We can calculate hydrogen or usually especially modes that don't overlap with the phonon spectrum. So the first benchmark, just to show you the power of this hybrid functional approach, let me show you. We did this in 2017 because I thought if you look at this diagram on the right, okay, these are different levels for the copper on silicon. It's an old problem, right? Copper, they use it to make a contact, and copper eventually get in, right? In the silicon crystal. And experimentally, the values are much better characterized, and I think it's well established that these values, they do come from the copper in silicon. And you see they spread. For instance, you have a donor level, an acceptor level, and then you have a transition from the 1- to 2-. So you change the slope from -1 to -2. And experimentally, you see the numbers are very relatively smaller range, especially if you compare what we know from theory. Look at the theory here in the middle column, right? In the theory, why? Because before we didn't have a hybrid function, or we didn't have a method that give you the right band gap, and the way to extrapolate what you get from a DFT within your LDA approximation to the real one is arbitrary. There was a lot of assumptions and so on. And you see the spread here. But if you actually calculate with hybrid functional, you get the numbers that are very close to the experimental data here, right? So these tell us how accurate we are, okay?
We have more 10 minutes.
Okay, I think I will finish in them. Zinc oxide, again, is the material that I started working a long time ago. And the idea is that these are crystals, they can make largest single crystal zinc oxide, high structural quality, has a band gap like that of gallium nitride. So in principle, zinc oxide could replace or even your gallium nitride, and you could buy cheaper LED lamps, right, nowadays, or lasers, right? The same crystal structure as gallium nitride, by the way. Easy to dope N-type. We don't actually know what is the cause of this unintentional N-type conductivity. Often you make it, you measure it's conductive, even though it has a very large gap of 3.4. And impossible to make P-type. Here's a question mark because so far we didn't find a way to make a P-type. And oxygen vacancies are often invoked as a source of N-type conductivity in this material. Okay. Possible applications, as I said, UV, light-emitting diodes, laser diodes, high-power electronics. But again, all these applications, the problem is we don't know how to control conductivity. So we look at the oxygen vacancies at that time, and despite these being also in textbooks invoking oxygen vacancies as a source of conductivity, because it is often reported that if you anneal the crystal in hydrogen or in oxygen or in vacuum, you can change the conductivity. The assumption was you can remove oxygen atoms or add oxygen atoms. But it turns out that the oxygen vacancies are deep donors. They cannot explain the conductivity. So the idea is that this kink here happens at 1 electron volt below the conduction band minimum. So the vacancy, when you have N-type, where your Fermi level is close to the conduction band minimum, your vacancy is just a neutral, it's inert, electrically inert. Then we look at all the other defects. The only defect that is a donor is zinc interstitial. It's in blue here. However, the formation energy in N-type is so high that you can ask, well, does it actually get in? You need the formation energy that are closer to less than 1 electron volt to be present in a measurable concentration, I would say. But it turns out that the zinc interstitial is also highly mobile. So the migration barrier is only 0.57 electron volt. That means that it moves even well below room temperature. So zinc interstitial is not stable. So the conclusion was the native defects cannot explain N-type conductivity. We look at hydrogen, and the reason is hydrogen was known to cause a conductivity in zinc oxide, but people had been looking at interstitial hydrogen, but interstitial hydrogen was also unstable. It couldn't move away. So you can hydrogenate your zinc oxide, measure it, you measure increasing conductivity, but then when you put in the shelf, the hydrogen goes away. Your conductivity goes back to normal. So hydrogen interstitial couldn't explain, and we found that the hydrogen actually assumed this very unusual configuration. It can replace oxygen, despite the difference in size. And they stayed there very close to actually at the ideal oxygen site. And the distance between oxygen and zinc are close to the hydrogen and zinc are close to the oxygen zinc equilibrium bond length. It turns out we call it a multicenter bond. The explanation came from a molecular orbital theory model. And it turns out that it is as stable as hydrogen interstitial in terms of formation energy, but its formation energy changes with the oxygen chemical potential because it replaces oxygen. So these tell us that the hydrogen interstitial may be hydrogen on the oxygen side may be actually a possible explanation for the unintentional n-type conductivity. The experimental verification came a few years later, and they found, measuring the frequency of the local vibration modes, they found it very close to what we predicted before. Right, so it was established. First we predicted and was later demonstrated. We also describe why nitrogen, why is it difficult or impossible to make n-type, and the reason is you cannot find a shallow acceptor in zinc oxide. And even nitrogen, which would be the most likely candidate, is actually it's a deep acceptor. The transition level is in the middle, almost in the middle of the gap. And what we calculate for emission and absorption, emission energies actually explain the experimental data. So I realized that I went over the time, and I don't want to rush. So even though I describe only zinc oxide so far, the plan was to discuss the titanium oxide, the idea, the relation between the vacancy now, which is a shallow donor, and the excess electrons in the conduction band, which actually form small polarons. You have a self-trapped electron. And the idea is that even though the vacancy is a shallow donor, it can actually bind or have a polaron bound to it. So you can see here, you have a vacancy which is doubly charged, 2+, but you can have it associated with one polaron or two polarons. So, but we argue that these are not a vacancy character. It's not a state from the vacancy, but it's really a complex. The vacancy is always 2+, and you can have one or two polarons. Similarly, you can have a polaron bounded to niobium, replacing titanium, or fluorine, also a donor, and I think even hydrogen. And this polaron is the one that explains this infrared absorption, usually associated with oxygen vacancies, right? And that's what we wrote a few papers on that discussing this issue. I was also planning to discuss the strontium titanate, the puzzling behavior that have been attributed to oxygen vacancies, where they said, well, it's a source of conductivity, where you think, oh, it's a shallow donor, levels near the conduction band, but also cause blue luminescence, which is deep level luminescence. So how a shallow donor can be also a deeper level, a source of deeper level luminescence. And we describe these in terms of oxygen vacancies with polarons bounded to it, right? And we actually developed a model for that. And finally, which is the most recent, where we discussed the effect of photoconductivity in strontium titanate, where they found that if you shine light with a photon with a little less than the band gap, you increase the conductivity by 3 orders of magnitude, and then you put it on the shelf, and this conductivity will last for a year, right? And we figure out that this is associated with an instability of hydrogen replacing oxygen, right? And hydrogen replacing oxygen give you a single particle level very close to the valence band, where you excite this electron to the conduction band, it becomes unstable and the hydrogen moves away, right? but only move away if you shine light. This is in this configuration coordinate diagram. So when you shine light, you go to an excited state of the hydrogen on the oxygen side, and then from here it moves away and the hydrogen just goes away, right? Here is the picture at the bottom, hydrogen on the substitutional side, and then when you shine light, it just move away, end up being a hydrogen interstitial next to a vacancy. And we explain the fact that they saw just based on this picture. So I'm going to just acknowledge my group here, which they are a source of inspiration, and they work really, really hard to make these papers happen, right? And just to summarize, saying defects is still an important topic in semiconductors. Control defects often dictate device applications. DFT is a powerful tool to study these defects and given access to properties that sometimes can be difficult to access experimentally. And now the advent of hybrid functionals, hopefully we will figure out a more efficient way of do these calculations, because it's still quite expensive, but they are quite accurate to describe defects. And defects will continue to play an important role in materials physics. Since we discover and develop new materials, think of 2D materials, the boron nitride, or the halide perovskites, and we want to use these materials in electronics, spintron solar cells. We really have to understand what's going on in terms of defects. Okay, thank you very much. Sorry for going over time by a lot. And I'll be happy to take any questions.
Fantastic, Anderson. Thank you very much for your really didactical seminar. Now the section is open to questions. Just raise your hand, and you can do your questions in Portuguese or in English. Doesn't matter. We can translate or make a hybrid section.
If you have any question regarding Delaware opportunities to work abroad, if you're interested in things that we are doing, we'll be happy to talk to you. Just send them an email to me, okay?
Guilherme raised the hand. Guilherme, you can open your microphone.
Okay. Do you hear me?
Yeah.
Yeah. Okay. So first, thank you very much, Professor, for the very nice talk. And actually, my question is about also strontium titanate, but more when we are talking about heterostructures, because nowadays I have seen many papers discussing the role of oxygen vacancies and these defects in the formation of two-dimensional electron gases or holes in such heterostructures. And actually, it's not that clear the role of such oxygen vacancies. And then they also talk about polar catastrophe. So I was wondering if you could shed us some light and discuss a little bit generally the role of oxygen vacancies in this type of phenomena. Thank you very much.
Sure. Yes, I think you're referring to now being studied a lot, the strontium titanate interface with aluminum aluminate, for instance.
Yeah.
Aluminum aluminate has a very large gap. Strontium titanate is still a large gap, but it's smaller. And when you have an interface where is titanium O2 terminated, right? And you see a two-dimensional electron gas at the interface, very high density. In principle, you could hold 10 to the 14 electrons per square centimeter, which is almost an electron per titanium at the interface. So it's very high. And there were different models put forward to explain it. One was that electronic reconstruction of polar catastrophe, where it was assumed that electrons from the surface would come to the interface. From the surface of a lanthanum aluminate would be transferred to the interface and give you these excess electrons, right? What we found is that the explanation is the other way around, is that the electrons, they should be at the interface in the first place because of the interface termination. And eventually, if you have a very thin layer of lanthanum aluminum, actually what you see is electrons being transferred from the interface to the surface. However, you still have, let's say, 90% of the electrons are transferred, only 10% stay there. So you still have a sizable amount. There was some groups talking about the point defects like oxygen vacancies in the strontium titanate being a source of conductivity. And we realized that it would not be the case. You would need, let's say, perhaps a too large electron concentration to be able to explain this effect. Right. Too large vacancy concentration to explain. So
okay,
we start to defect, but actually the interface itself. I can send you the articles we wrote. Be happy to do that. Yeah, just send them an email.
All right, Professor. Thank you very much.
Thank you, Guilherme. Gustavo, we have questions from YouTube as well.
Yes, so we do have a very interesting question here, Anderson. Eliel Marcelino is asking whether the same methodology that you have shown here could be used to study defects in liquid structures, like at very low flow rates. Have you seen anything like that? Is that possible?
In liquid?
Yeah.
Liquid. Yeah, that's an interesting question. Sometimes I think it's a little philosophical question, because if you think about a liquid or an amorphous materials, right, you already have a short-range disorder, right, and long-range disorder, right? And then it will be hard to have a reference to compute your formation energies. For instance, you take a total energy between a system with a defect. Let's say you want to remove an atom, okay, and you let the system, the atoms to relax around the defect. And then you take your liquid state or amorphous state, and the total energy difference will give you basically how much does it cost to form. However, it will be hard to define your reference state. And perhaps you need a statistical approach to actually define these reference state. That's how, now if you have a gap, a large gap that's well defined in both materials, you can still see levels in the gap. But again, and perhaps if you see levels in the gap, since transition levels, they do involve a total energy difference, and the energy difference of the reference level may cancel out, you may still be able to talk about transition levels, but I'm not sure about formation energies. You may be wrong by a lot. And yeah, so that's maybe, I'm not sure if I answered your question as you were expecting, but yeah, it's an interesting question. It has been discussed in the literature. So.
Fantastic. Thank you, Anderson. We have time for one or two questions. Gustavo, you have one. Unmute your microphone, Gustavo.
Okay, sorry for that. So this is my question now, Anderson. Very, very nice talk, and very easy to understand, very well prepared. So Anderson, I'd like to hear your comment on similar to the previous question, but on the applicability of this kind of defect calculation to 2D materials or surfaces, as you wish. So what do you think about using this kind of methodology to study defects in these cases?
Okay, Yeah, that is again very good question. By the way, yeah. So when you look at defects in two-dimensional materials, right? You using a supercell, okay? You need to define what we call a slab geometry, right? So you have a vacuum in one direction, and you have a material in the plane, right? In the two-dimensional, perpendicular to your surface. And then you say, okay, imagine you have boron nitride, has a very large band gap, and when you create a vacancy or add some impurity to it, you end up with levels in the gap, let's say states in the gap, right? You see single particle states in your calculation in the gap. And the problem is, I say, okay, this in principle is a neutral defect, right? I didn't add or remove an electron from this state in the gap. If I try to do that in the supercell approach, you have, when you remove an electron or add an electron, you have to add, basically the codes they do that, they add a neutralizing background, which is equivalent to shifting the average electrostatic potential to zero, basically. So this neutralizing background goes over the whole supercell, including the vacuum. So this will cause problems converging your total energy or your total energy differences as a function of the thickness of your vacuum layer, right? So in a way, you don't know how to define the formation energy, because if you change the thickness by 2 angstrom, instead of using 15 angstrom of a vacuum, you use 17, you have a different number. And this doesn't converge. It doesn't converge because you have an electrostatic interaction, because you look at the neutralizing background doesn't really match the charge density associated with your defect state, right? The wave function square. So these will cause dipole or multiple interactions that would make it difficult to converge, and at the end you cannot say anything about the position of the transition level in the gap. So there are ways nowadays to correct this, and this is still an area of research, right? It's not well established. It has to do with the screening, the charge that you added or removed. And I would say, I can point it to you to the recent papers by a group in Switzerland, in Japan, dealing with this problem. It's not as straightforward as we have, because you can think of, if you have a defect in a bulk, when you add an electron, or when you add a neutralizing background, right? Let's say if the neutralizing background is negative, it's like adding an electron to the conduction band minimum, where it's an extended over the whole crystal. So more or less, it seems reasonable, right? Because but you have a problem when you have a vacuum. Yeah. So the same problem is for the surface as well.
Thank you, Anderson. I don't know, but we don't have more time. I will switch to Portuguese. Obrigado, Anderson, pela participação aqui com a gente no Brasil. A apresentação muito didática, parabéns mesmo. Muito gostoso assistir. Obrigado mesmo.
Obrigado a vocês. Desculpa o barulho aí, é que
Imagina.
Tem um pessoal aqui perto cortar grama essa hora.
Obrigado, Gustavo.
Tá. Ok, thank you. See you guys. Yeah.
Valeu.
Obrigado, hein? Tchau, tchau.
Obrigado, Anderson. Pô.
Lembrando que semana que vem a gente continua no Colóquios da Nano com o professor Leonardo Machado, lá da Universidade do Rio Grande do Norte. Dá uma olhadinha aí no